Welcome viewers to the 18th lecture of the course Non-Traditional Abrasive Machining Methods, including ultrasonic machining, then abrasive jet machining and abrasive water jet machining, and we have already completed ultrasonic machining and abrasive jet machining. We have completed I think 2 lectures on abrasive water jet machining also, and today we are going to proceed with some numerical problems in abrasive water jet machining. So, let us proceed. This one we have already solved in the previous lecture. So, I am skipping this. Okay. So, let us see. An abrasive water jet machining company makes glass mementos. Okay, glass mementos by grooving the map of India on plain glass samples by abrasive water jet machining, and finds that abrasive cost in the market has increased by 20%, but the machine overhead, that means hourly machine cost for electricity, labor, lubricants and AMC etc., that has gone down by 10%. Each part was taking 4 hours previously. So, in response to this price hike and coming down of the overhead, he now reduces abrasive consumption from 1 kg per minute to 0.8 kgs per minute. So, that is quite natural. Prices of abrasive have gone up, and so he reduces the consumption of abrasive. The water mass flow rate remains constant at 3.79 kgs per minute. The previous grooving velocity is 300 millimeters per minute. Okay, previous grooving velocity is 300 millimeters per minute, and it can be changed now. Previous abrasive cost is 400 rupees per kg, and previous machine overhead is rupees 200 per hour. Okay, that is understood. So, lot of data, and first of all it is a question of grooving. Do we know anything about any any relation between grooving and grooving depth and something else, etc. So, let us have a quick look first at that. And what was the question? Find out whether the company would be able to keep the manufacturing costs per job the same. Oh, that is it. This expression is appears to be something that we have come across in the very recent past. What is that? I think you will recognize this particular expression, r into eta square by 1 plus r, I mean eta by 1 plus r whole square into p to the power 3 by 2 into 2 by root over rho, etc. And okay, all these are constants for which we will definitely find out what are the values to be taken. Then pi by 4 d square is the cross sectional area, etc. So, this is a well known expression that we have coming across, but these are the newcomers. These are the newcomers. How are they coming in? So, probably it is because of this. Let us write down the previous expression that we had derived, MRR equal to 1 by specific energy of the job material, okay, into, if I remember correctly, it was pi by 8 in all sorts of constants, which I am just putting it together like this, constants, and there was d0 square multiplied by r into eta by 1 plus r whole square into p to the power pw to the power 3 by 2 multiplied by 2 by p w rho w root over, etc. Now, how does it compare with the grooving equation that we had written down? It comes in here. Instead of writing MRR, simply let us write down the volume of material removed multiplied by the density, and after that we will be sorry, we do not need to bring in density. This is material removal rate volumetric, and let's first write down this must be equal to the grooving depth d, okay, dg, write down here dg multiplied by vg, okay, velocity of grooving, depth of grooving, cross section of the groove, sorry, width of groove, let's write how much, w, width of groove, that is it. Once we write this and keep dg on this side, therefore, dg will be equal to, we write dg equal to, and put all these things underneath, dg, sorry, vg into wg, and in order to keep them company, we bring it here, S job, that is it, and we get the expression for depth of groove. So, that is what, let us come back to the screen, that is what is written here, you know, all sorts of equations, cross sectional area r into eta by 1 plus r whole square into comes our, you know, well known characters, the 3 characters, wg, vg, S job, and other things are, you know, as mentioned before. So, it is nothing very, you know, something very similar to what we have been discussing up till now. The depth of groove is related to the other terms in abrasive water jet machining in this particular form. So, our question has been given. Let us have a quick look once again at our question. What are the, you know, stumbling blocks here? No problem, abrasive cost has increased, machine overhead has decreased. Now, the abrasive consumption has changed from 1 kg to 0.8 kgs per minute, and the water flow remains constant at 3.979, and the previous grooving velocity is given and can be changed now, and the previous abrasive cost is 400 per kg, and the previous machine overhead is 200 per hour. Now, the question is, would the company be able to keep the manufacturing costs per job the same? Interesting. Let us see how it can be done. Okay, the operator has to get the same depth of groove. Naturally, if the part has to be the same, the groove depth has to be the same and has to cut the same length of groove on each part. Yes, of course, if it is the identical job, the length of groove is the same and the depth of groove should be the same. Hence, groove depth has to be made same for both. As for all the other terms remaining, as all the other terms are remaining constant, in order to have the same groove depth, we have this particular expression. What are we doing here? All the terms which are changing from case 1 to case 2, we have, written them down, and all the other terms we are assuming they are cancelling out from the 2 sides. Pressure of the water jet, are we changing it? No, so it gets cancelled. Density of water, it gets cancelled from 2 sides. The same material is being cut, so the specific energy gets cancelled. So, like that, so on and so forth, we simply have these terms and they have to be equal. Why? Because the groove depth has to be the same. So, R1, that means loading factor for the first one, that means m dot abrasive by m dot water divided by 1 plus I, etc., etc., etc. Velocity, the first velocity is definitely going to be different from the second velocity. You may ask me, why? Why don't I keep the velocity the same? You will get to know as we proceed that the velocity has to change. Okay? So, let us see. So, in fact, from here itself we can understand if the groove depth has to be the same, I am sorry, here itself you can find it out. If the groove depth has to be the same and r has changed, velocity has to change in order to keep these two same. Why has r changed? Because he has reduced the abrasive mass flow rate from 1 kg per minute to 0.8 kgs per minute. So, r is changing. So, naturally, v has to change. So, let us have a quick look. 1 kg by 3.79 kg, which is the water mass flow rate, abrasive mass flow rate, divided by 1 plus r whole square, which means 1 plus 1 by 3.79 whole square multiplied by the speed of cutting, 300 millimeters per minute. Speed of cutting, speed of grooving must be equal to the second loading factor, which is 0.8 divided by 3.79 divided by 1 plus r whole square into this is the unknown, from which we find out that he has to employ this particular speed. He has no other option. So, is this understood? Everything else is known. We put in the values and we can get to know the velocity of grooving which he has to employ in order to attain the same depth of groove. Once this is understood, so hence he has to employ this velocity. The second condition is that the length of the groove is to be the same for both the parts. The length of groove is to be the same for both the parts. So, we understand velocity of grooving in the first case multiplied by the time of grooving must be equal to velocity of grooving in the second case multiplied by the time of grooving. That means total length of groove is equal to total length of groove. That is understood. That is very good. 4.59 hours. Okay. T1 is known. How much was T1? Oh, each part was taking 4 hours previously. Okay. So, we have put it here 4 multiplied by the grooving speed is equal to the second time and the second grooving speed. Grooving speed having been solved before, we get the time 4.59 hours, and after that it is just you have to finish calculating the costs of manufacturing. Let us see, let us have a quick look how they are calculating it. First of all, this abrasive cost 1 kg of abrasive costs 400 rupees, and therefore, so this is cost per minute, is it? Costs per minute. Abrasive cost is 1 kg per minute multiplied by 4 hours, because one part is taking 4 hours multiplied by 60 minutes plus 4 hours multiplied by machine overhead is equal to 96000 plus 800. Now, what is this 800 coming? Where is this 800 coming out from? Let us see whether there are any other costs. Previous machine overhead is 200 rupees per hour, okay, and abrasive cost is 800. Are there any other costs? Okay, let us see. Oh, I understand. This one, the first term is 96000 and the second term is 800, and they add up to 96800. Next one is abrasive cost per minute is, sorry, this was abrasive cost per minute, and abrasive consumption per minute was 1 kg, and that is why it is multiplied by 60 to find out the cost per hour multiplied by the total number of hours. Okay, the second one is more tricky. The time is 4.59 hours, and the cost of the consumption of abrasive is 0.8 multiplied by the cost of abrasive per kg multiplied by the increase in cost of 20%. So, 1.2 multiplied by 60 to make it per hour, and then multiplied by the total number of hours. And next is the machine overhead, where the cost machine overhead cost has come down by 0.90% and 10%, and the total time of use of the machine is 4.59, and therefore is much higher. So, the answer to the question is that even if he has reduced abrasive cost to 0.8 of its previous value, and even though the machine overheads have come down by 0.9, I mean by 10%, still he has to spend lot more in order to machine the second part. Okay, this is the answer, because this cost is coming out to be much higher. Okay, let us take the next one. Numerical problem on water consumption. This was what we were discussing. So, a factory is carrying out a specific grooving operation on metallic parts by abrasive water jet machining, in which abrasive consumption rate is 0.6 kgs per minute. Okay, that is understood. Abrasive consumption is 0.6 kgs per minute. Water mass flow rate is 3.79 kgs per minute. The factory runs the machine continuously for 8 hours per day. This year, a severe water shortage occurs and the factory is not permitted to use more than 1500 liters of water per day for abrasive water jet machining. So, the idea is very clear. 8 hours of work was being done previously, and now suddenly it is shortened because they cannot use water more than 1500 liters, and therefore, the water flow rate, but not the water flow rate, the number of hours of work, it has to be shortened. Why? Because the water mass flow rate cannot be changed. If it is 3.79, even if you have a drought, you cannot reduce the water consumption. So, you can run the machine only perhaps for reduced number of hours. That calculation will tell us. Okay. The management takes a decision to change the abrasive mass flow rate and run the machine for as many hours as possible in one shift per day, and thus finish the same number of metallic jobs as done in 8 hours of work per day previously. So, what they have planned is that previously with 8 hours in our hand and with 3.79 water flow, we were using 0.6 kgs per minute. Now, we cannot use it for 8 hours, maybe we can use it for 5 hours. So, increase the abrasive mass flow rate, so that we have enhanced or increased machining rate, so that even if we have 5 hours, we can finish the job of 8 hours in the previous case in those 5 hours. This is the problem, very simple. So, let us see how it can be done. Questions are, for how many hours can the machine be run per shift with changed settings, and find the changed abrasive mass flow rate for the changed settings, and what is the value of the loading factor R with the changed settings. What is the assumption? Assumption is that groove width remains constant for any setting, which is not really true, but for all practical purposes we can assume this. And R is the loading factor, it should not be set more than 1. Now, are we changing R? Yes. If water mass flow rate is not changing, but the abrasive mass flow rate is changing, R has to change. And 1 liter of water weighs 1 kg, and all standard assumptions of abrasive water jet machining, they are applicable, and all loss factors to be taken as unity. So, let us proceed on to solve the problem. In this problem, the company has only 1500 liters of water for their machine, while the consumption of water is 3.79 kgs per minute. So, this means that the machine can only work for 1500 liters, which is your capacity per day, divided by 3.79 into 60, which is the consumption per hour, equal to 6.59 hours per day. So, you can use this machine for 6.59 hours per day now. You cannot use it for 8 hours. Now, in order to cut the 8-hour job in 6.59 hours, grooving speed needs to be made higher. Grooving speed, naturally, if you are cutting, if you are grooving, and if this grooving is taking less time, that means your speed is increasing. So, grooving speed needs to be made higher. Grooving length is the same, you are cutting the same job, and mind you, you have to produce the same grooving depth also. So, we have two conditions to satisfy. We have a new velocity expression now, and we have a new grooving and we have to maintain the same grooving depth. I hope you can read this. Suddenly it has become smaller font. So, if V1 be the old and V2 be the new grooving speed, in that case we can say T1 into V1, which means the length of groove is being made the same. You are cutting the same job, the length of groove is the same, and therefore, T1 into V1 is equal to T2 into V2. So, time for the previous one we already know, it is given to be 8 hours multiplied by the velocity of cut in the previous case. Now, what was the velocity of cut in the previous case? Suppose I do not know that, whatever. So, in the second case, the time of grooving was reduced to 6.59, and therefore, we have at least a ratio of the speeds available with us. What is that ratio? V1 by V2 is equal to 6.59 by 8. Now, in order to cut the same groove depth, the job is remaining same, the groove depth has to be the same, and once again we remember that in the expression for groove depth there were so many other terms, but none of them are changing. Okay? Just to remind you, cross section of the water jet is not changing. I mean, water jet of water is not changing, then pressure is not changing, density of water is not changing. So, we absolutely do not have to bother about the other terms, but these terms are changing. Okay? Loading factor is changing, velocity is changing, therefore, groove depth has to be now kept the same. Okay. Let us see, it is becoming smaller and smaller, but hopefully up till this point we have the same thing written down once again, and I hope you can read this. It is written here, we have simply put in the values. Let us quickly check whether the correct values have been kept. Yes, R1 is equal to 0.6 by 3.79. 0.6 was the previous abrasive mass flow rate, and water mass flow rate remains the same, which is 3.79, and we are considering that x is the present mass flow rate of abrasives. What about our velocities, grooving velocities? We do not know the grooving velocities, none of them, neither V1 nor V2, but we know their ratio. V1 by V2 is equal to 6.59 by 8. So, V1 and V2, their ratio we are replacing by 6.59 by 8. 6.59 has been written on this side and 8 on the other side. That is okay. 1 plus r whole square has also been written, and since x is the abrasive mass flow rate, so we have x by 3.79 equal to r, and 1 plus r accordingly written there, so that after we crunch the numbers, that means we use a calculator or Excel file or whatever, we have 4.8 divided by 4.39 whole square into 6.59 equal to x by 3.79 plus x whole square. So, obviously, we are going to have a square term appearing, and that means we are left with a quadratic expression, a quadratic. Okay? 4.8 x square minus 90.616 x plus 68.94 equal to 0. Shall we have a quick look? If internet connection is available, we can have a solution to this one. Let us see. Whoa, okay, we can do without this. We do not exactly need it, because I have solved it here itself. So, coming back, we see that if we solve this quadratic equation, we have 4.8 x square minus 90.616 x plus 68.94 equal to 0, and if you have a quadratic equation solver, you can simply use that. Of course, if you are permitted to do that in the exam, if you are not permitted to use that, you can simply use x is equal to minus b plus minus root over b square minus 4ac divided by twice a. So, with that sort of calculations, I have not included these calculations because you can do it yourself very easily, and therefore, x in my case was coming out to be 0.79. That means the consumption of abrasives will be increasing from 0.6 kgs per minute to 0.79 kgs per minute. Okay. And if you find out the ratio of the new abrasive consumption rate to the to the mass flow rate of water, you will find that the R value will come out to be 0.208. Okay. So, I hope that you will agree with me that the question, when you start with it, looks quite formidable, but it is absolutely logical, and it is based on a hard foundation of technological facts. That is, if you have to change over from one setting to another, remember that groove depth has to be maintained the same, cutting total groove length has to be maintained the same. So, groove depth and groove length have to be the same, and velocity, as it affects the groove depth, and what do you call it, as the loading factor affects the groove depth. So, they have to be properly taken care of, so that you have you can maintain the same groove depth and the same length of groove. Okay. So, I will end this discussion with a small example from MCQs. In an abrasive water jet machining setup, the abrasive addition is a constant 200 cc's per minute and water flow is at 3 kgs per minute. The machine operator replaces original abrasives of rho equal to 4 grams per cc with a cheaper variety. So, in that case, the MRR will increase, MRR will decrease, MRR will remain the same, and we cannot say, because theoretical prediction depends on the hardness. Okay. So, let us try to find out what is being talked about. If abrasive addition is at a constant volume rate, then mass flow rate is also at a constant rate. But the moment you are changing over from one abrasive to another, the rho is changing, which means that the abrasive mass flow rate is going to change. So, you can quickly calculate what is the changed mass flow rate, and accordingly we can find out whether the term R by 1 plus R whole square, whether it is going down or going up. If it goes up, then the power available for machining is higher, and if it goes down, the power available for machining will be lower. So, MRR will accordingly increase or decrease. The change in the choice of the abrasive will bring about a change in the power delivered by the abrasive phase, which is actually the power responsible for material removal. So, half m v square is equal to half R into m dot W into 1 plus R whole square multiplied by velocity square. Okay. So, we have calculated this term because it is easy to calculate, because all the other terms are constants, while R by 1 plus R whole square has to be calculated. So, R has a value of 0.2 into 4 by 3 in the first case, which is 0.26667, and in the second case it has 0.20667. Okay. You might say, how are we doing it? Well, in the first case you can find out multiply the density with the constant volume rate of addition and find out an expression of mass flow rate. In the second case also, with the change density you can find out the mass flow rate and then calculate R. Okay. For the time being I am leaving that to you. So, if we calculate the R value, we find that the representative of R by 1 plus R whole square is coming out to be, in the first case 0.166 and in the second case 0.14, and therefore, in the second case the MRR will decrease. MRR will decrease. So, I will stop here. If you have any doubts, you can definitely ask me while the lectures are going on. So, this is the end of our 18th lecture. We will continue with the next lecture next time. Thank you.